You're chairing? Who's the chair? You're the chair. Okay, shall I start? Yeah. Okay. Right. So thanks for inviting me to this very nice meeting. Thanks to the organizers. And so that's the title I choose, but it may be a bit misleading. So I will start by telling you what this talk is not about, and then I'll talk about gravitomagnetism in structure formation down to galactic scales with what I call a post-Friedman approach, using a code, both Newtonian and body simulations, and a code, a GR code, which is called Gramsci's. And then finally, in this part of the talk, I will illustrate some recent work based on the illustrious simulations. And then I'll pass to a full GR description, where I use a toy model for a cosmic web over densities, voids, and filaments, which leads to quasi-spherical collapse. This is done with the Einstein toolkit, which is a full GR code. And then I will finish the talk with some work in progress. Right, so standard ΛCDM model. So this is based mainly on 3 ingredients. The first 2 are, as we have been heard in this meeting several times, by Friedman-Robertson-Walker models, and then on top of that we add perturbation, and the third ingredient will go on in a moment. So looking at the sky, we see relativistic perturbation. These are the pillar for constructing CMB theory. And we also go to nonlinear relativistic perturbations when we want to treat non-Gaussianity. And so take-home message number 1 is very important to consider these second-order perturbative effects. And this is an example of a paper now long ago where there are these effects that needs to be taken into account to disentangle true GR effect from non-Gaussianity and bias. But I'm not going to talk about perturbation theory today, okay? So the third ingredient is that to study fully nonlinear structure formation, we use Newtonian theory in cosmology, okay? This is mainly through n-body simulation or approximate nonlinear techniques like 2LPT, okay? So on this basis, we have the so-called concordant models of ΛCDM. That's it. Not quite a concordance. Anyway, so therefore, in summary, when we describe the units on very, very large scales, this is this GR description, but if we zoom in, we use a Newtonian picture. So, so my question is, or there are many questions on ΛCDM, but the one I address today is if the third pillar of ΛCDM using n-body simulation, Newtonian n-body simulation is good enough, okay? Because we are in an era now where we have much more data, we need precision cosmology, we want to also be accurate, as we have said at the beginning of the talk, and one way to be accurate is perhaps if there are tiny GR effects in structure formation that we are neglecting, we may misinterpret what we see, okay? Right, so let me talk about gravitomagnetism. So basically in GR, if you have moving masses, you have the same effect that if you have moving charges in electromagnetism. This generates what we call a gravitomagnetic effect, okay? It's associated with rotation, but not only. In general, it's associated with any matter motion, okay? It's important, of course, in strong field, like neutron stars and black hole, but it is also important in weak field. And in fact, this is an effect that is measured around the Earth. The Earth rotates, and tiny is a tiny effect, but it has been measured, okay? So let's keep this in mind. And with this information, let's move on and introduce quickly this, what I call post-Friedman approach, which basically is an approach where instead of expanding my Einstein's equations using perturbation theory, I use a kind of post-Newtonian or post-Minkowski approach. However, the crucial thing, and that's why it's post-Friedman and not post-Minkowski, is that the background is Robinson-Walker, okay? And let me say, so that this was, the formulas for all of these was developed in that paper with the student Irani Milillo and a couple of postdocs. And to cut a long story short, I developed this now more than 10 years ago. And this was developed in a sense as something that was in the back of my mind from the mid-90s, where we were completely neglecting gravitomagnetic effect and trying to build with Mother Race a certain approximation. And then Lev Kaufman and here our friend present here developed a very nice paper which clarified aspects of this story, in particular saying that how important is to consider this gravitomagnetic effect, okay? So basically I call zero post-Friedman the leading order of this expansion, where you get from Einstein's equation just the standard equation for Newtonian, in the Newtonian approximation, but interpreted in the GR context. So you work with the dynamics in Newtonian, but the gravitational field is a perturbation of the metric, okay? But in addition to this, you get an extra effect. I'm going to go there. Let me explain better this point, that this is not just post-Newtonian, because in a post-Newtonian, true post-Newtonian, you could only apply that inside the horizon, right? Because post-Newtonian imply small velocities, right? But in cosmology, we have the sum of two. From this Newtonian perspective, we have two velocities: the bulk, the Hubble expansion, which you don't want to limit, and peculiar velocities on top of that, okay? So, moving on, schematically, think in this way, so that if you consider all of GR, you can linearize it at the core there, and there is a part of the linearization coincide with with Newtonian theory. You can go second order in GR, but you can do this post-Friedman expansion, and then the post-Friedman expansion includes in full linear theory, linear perturbation theory, and part of second order, okay? So, as I said, it was developed by that paper, and at leading order includes the standard Newtonian equation. This gives the dynamics. However, beyond leading order, linearizing the equation gives a first order perturbation theory, okay? The first effect that comes out from this expansion is 1 over c cubed. So 1 over c squared gives you Newtonian theory, okay? Extra effect, which will be really partly second order, you can call it as 1 over c to the fourth, but the leading extra term is 1 over c cubed, and that comes from the nonlinear, from the 0i part of the metric, okay? So, bottom line, if you expand the 0i Einstein's equation using Poisson gauge, what you recover is an equation where the right-hand side is built out of nonlinear Newtonian theory, no approximation on the right-hand side, okay? So is the density, rho, which appears as a rho bar, the background multiplied by 1 plus delta, no approximation, times the small velocity, okay? The velocity is 1 expanded. This is a 1 over c expansion, okay? However, from the 0i Einstein's equation in Poisson gauge, this gives this equation for what I call Bn, which, because it's the linear order in this gravitomagnetic vector field, I call it n to remind ourselves that this is sorted purely by Newtonian terms, okay? So then, if you look at this curl of the right-hand side, you can split this into 3 parts, and you realize that the vorticity itself is totally subdominant. For comparison, here you have the linear and nonlinear matter power spectrum of a standard vanilla lambda CDM cosmology, and the two top are the two main contributions to the source term. Okay, and these are stronger purely because we are in the nonlinear regime, and so delta is nonlinear. Okay. Then we can extract this vector potential from the simulations. These was using pure Newtonian simulation, therefore, and you get this vector potential, which is of the order 10 to the minus 5 of the scalar potential in terms of power spectrum. Okay, so the ratio of the potential is of the order 10 to the minus 5 in terms of the power spectrum. Okay. So an important point to make is this. So although this is a small effect, you go wrong by 2 orders of magnitude if you try to get this through second-order perturbation theory. Okay? I can explain that more in detail if you have questions later. Okay? But that's what you get. 2 orders of magnitude larger than what you get in second-order perturbation theory. Simply because you are in the fully nonlinear regime for the matter distribution. Okay, and then we did a series of other papers, and in my opinion, this is something that should be explored more. But let me point out in particular that we also applied this in f of r gravity, in which case this ratio of the vector and scalar potential is different than in GR. So in a sense, this could be a way. There are no free parameters here, except if you do, if you do f of r, you will get the parameters of f of r, but no phenomenological parameters. Let's say, then you will get a different signature from GR, and so this could be used in that sense, okay? All right, so then, fast forward to the last 5 years, we extended this type of approach using what is a code which is called Gramsci, which was developed in Durham by Bajuli and his student Christian Barrera. And so Gramsci is an n-body code, but is built on full GR, except that it uses what is called a conformal approximation. I'm not going to go into details, but it's a very reliable. Essentially, it neglects gravitational waves. Let's simplify the story, okay? So it's very reliable for what we need to do. So, and then you do the standard simulations. This is a matter field. To the right, you have the standard divergence of the velocity field. But you can extract the velocity, vorticity, and the vector potential magnitude. And that's what we did. And again, in terms of power spectra, with this work, we were able to extend a bit to more nonlinear scales. And again, the thin lines in these plots are the results from perturbation theory. And the thick line are those coming out from the simulations. And these plots refer to different redshifts. Okay? And let me anticipate something I clarify here more later. There is a problem in doing this simulation because basically what you want, of course, is that you want to match your result with the prediction of perturbation theory on very large scales, okay? Because on very large scales, the second-order perturbation theory is reliable, but then there is a problem with the simulation box, but I'll talk more on that in a moment. Anyway, so this is just to show different halos. So this is a very large, this is a chunk of the simulation concentrated on a small halo, okay? And here in the plot, we have a visualization at the 0 redshift of the scalar and the vector potential and the density field to the left. And if you consider larger halo, the effect is more diffuse, and of course, if the halo is very, very large, then it's hardly visualized, and the effect is very, very diffuse, okay? So then this is a more recent work, which was mainly the work with William Beordo, which is a PhD student of Maria Teresa in Turin. We just finished in July, and he visited me, and we developed this work, which came out just 2 days ago. And basically, the idea was to repeat this same story, again, this time using Newtonian simulations, but those of the Illustris TNG suite, which go to smaller scales, okay? So William is, by the way, looking for postdocs, so he's a very good student, and therefore, if you are interested, get in touch. Anyway, so the simulation that we use are 3 out of the full set. Basically, one is 35 megaparsec inside, one is 75, and the other is 205 megaparsec inside. Okay, so then go back to this lack of power problem. So the thing is that it is a well-known fact that if you make smaller box simulations, then you end up with a lack of power on the larger scales in that simulation box. And these, the 3 lines here, the thin line is the linear power spectrum, and the color lines are red for the larger scale simulation, blue for the medium one, 75, and green for the smaller box. Of course, with the smaller box, you can go further down in smaller scales, but you can see that there is a lack of power. Okay? This is well known when you do a simulation for the matter field or the potential, but it gets exacerbated a lot when you do this exercise for a vector field. So on the right, you see that the line color, the bottom part are the velocities, which had to be multiplied by the density field to get so the right is the power spectrum of the momentum field, and then you can see how much the problem is exacerbated. However, and the same problem was found in this paper by Park, Alvarez, and distinguished Professor Bond here, and when they were looking at SNe Ia, and they suggested a method to actually solve the problem, which we applied, and the correction method. And then you can see that using the correction method, the 3 power spectra on top align very well, and this allows us to go to a smaller scales. And the thin line here, there are actually 2 thin lines in gray. One is the second order prediction, which underestimate a lot the prediction, and the dash thin line is what you get producing this gravitomagnetic field using halofit, which slightly overestimate, especially on the smallest scales. And the bottom panel is just the same, normalized to the linear power spectrum, okay? To emphasize even more how the second order perturbation theory underestimate the effect, okay? And then these are the results at z equal to 0. On the top is the density field. This is for the 35 megaparsec box. To the right is the vorticity field. To the left is the scalar potential, and to the right bottom is this gravitomagnetic potential. And this is really what I love, is a superposition of the lines of the magnetic field, gravitomagnetic field, superimposed on the scalar potential field. And so you see how this gravitomagnetic field creates these vortices, etc. Okay? Okay, so now let me go back 10 years again, and let me talk about full numerical relativity work, okay? And the cover of this physics world issue was done by a student of Glenn here, okay? Because let me tell you this nice little story. So the story is exactly 10 years ago, I was working for very long with Eloisa Bentivegna, who was a poor postdoc in Sicily for long doing this numerical relativity simulation. We were almost ready to to go on the archive, and then bang, a paper by Glenn and collaborators comes out and say, oh no, we finished the paper, put it on the archive, and then I emailed that gentleman there and said, which at the time we just knew each other a bit, but we weren't yet friends as we are now. And so I explained, look, it looks like your paper is going to go on PRL, or that's your ambition. You have a 4 pages paper written in PRD style. So maybe that's your ambition. That's our ambition as well, as you can see now with our paper on the archive. Just I think it was like 3 weeks later, 2 weeks later. It was all before. It was really just before Christmas, right? And so why don't I, and then I made this suggestion, why don't we try this? We convince the editor that we both deserve publication and we can go back to back in PRL. And we managed that. And that's it. So this was the result of my paper with Deloisa and the paper by Giblin, Mertens, and Starkman. So the question at the time, which we wanted to cut through, was that of back reaction. So in the previous 10 years, after the discovery of the acceleration of the universe, there has been very much work, partly motivated by Thomas Buchert formalism for averaging and back reaction, on trying to explain the acceleration of the universe through back reaction effects, okay? And then most work was done with perturbation theory, because in this Buchert formalism, you get some extra term in the Friedmann equation, which, however, are like free source. You have to make some assumption to construct those sources, okay? And lots of work have been done in that way. But with numerical simulations, you don't need any assumption. What you do is you simulate your full GR nonlinear distribution, let it evolve, and measure how the box expands, and then it's a yes or no answer, right? So, and bottom line is, okay, before I go to the bottom line, let me, for those that are not aware enough about the back reaction, the basic idea is schematically illustrated by these phase plots, okay? So if you assume flat cosmology, lambda CDM, Friedmann constraint give you omega n plus omega lambda equal to 1, you derive an equation for omega lambda, and that is just the logistic equation, is called, which describes the evolution from a nonlinear unstable point, which in our case is Einstein de Sitter, to a de Sitter equilibrium point, okay? So the question for back reaction is there an effect that basically reproduces the same effect, the same result, without actually assuming any lambda, an omega back reaction, let's say, okay? So that's omega back reaction, okay, from the simulation box, assuming various initial conditions. And so even with the most extreme and unrealistic values of perturbation in the initial data, you can, this omega q is really an omega density parameter that affects the omega density parameter you can construct. Okay? And again, this is, you can see how small the effect is. Even the most extreme case is 10 to the minus 5. But again, small doesn't mean perturbative. Okay? The perturbation prediction is the dashed line. Moving on, fast forward to more recent time, many questions were left from that work. Eloisa went her way, so I didn't have collaborator working on this until I got Robin Munoz as a student, and I put her to go back to this kind of project, and Robin finished her PhD now almost 2 years ago. So the idea here was to use pure initial condition from a pure growing mode, which we were, in the first paper, we were not attempt to do that, okay? And so let me explain a bit more what we were doing. The idea is to construct a toy model of a cosmic web. So in the following sense, a cosmic web consists of 3 main elements, let's say, an order density, filaments connecting the overdensities and voids surrounding them, okay? How you can make a toy model of that? Because the idea of this toy model is this. If you make spherical, it's too simple, okay? No tidal field. If you do this to look for small GR effect using a full simulation is very, basically it becomes impossible to, it becomes really the needle in the haystack, right? So we assume that we describe cosmological perturbation using this RC variable, which is used in inflationary modeling, for instance, okay? Is a curve of perturbation, and we simply assume that there is an amplitude multiplying this function, which is the sum of three sinusoidal with the same wavelength in three directions. Now, why this describe what we want? So just to show the geometry of the distribution, that's the plot of this function for these various values of a constant, okay? You may don't know, but if C is equal to 1, you get a tetrahedron, okay? If C is larger than 1, of course it can be between 1 and 3, no more than 3, you get a quasi-spherical object, which will represent our overdensity. If C is smaller than 1 and positive, you get bridges. And remember, this is sinusoidal, which is the basic boundary condition for our simulation boxes. So you have bridges connecting the different overdensities. And if C is negative, then you get the boundaries of a void. Okay. So, as I said, we construct initial condition from starting from linear theory for I think in which case for you have just a dust model, you have one single degree of freedom, and everything is described by this RC, and this RC is related to the three-Ricci scalar, is simply a potential for the three-Ricci scalar. And this RC is constant in time, okay? And so you can write your, instead of using the traditional second-order equation for delta, you can use a first-order inhomogeneous equation for delta, where you use this useful fact that R is a constant, and therefore you get an inhomogeneous equation for delta. You get the two growing mode out of this equation. The growing mode is the one sourced by the per particular solution, and the homogeneous solution is the decay mode, okay? We take just the growing mode, construct the metric and the extrinsic curvature, and then we construct but now we want to do numerical simulation. So we take that metric as our initial metric, and the code doesn't know that's first order, okay? You know that you constructed that at first order. You just have a metric, you have an extrinsic curvature correspond to that, but then you can compute in full nonlinearity the three-Ricci scalar, and then you plug into the Hamiltonian constraint, you plug it in the Hamiltonian constraint, the full three-Ricci scalar. K is the extrinsic curvature, which is basically extrinsic curvature Kij is minus Hij that was mentioned by Dick on Monday, right? It's just a different language in numerical relativity. And so with those information, then you use the Hamiltonian constraint to actually build the corresponding density field, okay? And this is how you built the initial condition. And this is just a similar plot to the one before, but plotting for delta 001, okay, just to give you the idea of the isodensity surfaces, okay? An overdensity surrounded by filaments and surrounded by voids, okay? So that's a different plot of the density distribution. Okay, so our goal here was very simple in a sense. We wanted to check if the center of the overdensity actually evolves as a top path or not, okay? Despite the fact that there are all these tidal effects surrounding it, okay? So from a GR perspective, a top path is a closed Robertson-Walker model matched to a Schwarzschild hole, okay? Surrounded by flat Robertson-Walker. And in other words, therefore, a top path is exactly the same as the Oppenheimer-Snyder collapse, okay? except that you put this in a context of cosmology, and you have an initial expansion, a moment of turnaround, and then the recollapse. Okay? So that's the top path, evolution, and it is traditional to compare the evolution of the full nonlinear density field of this top path. As I said, is a closed Robertson-Walker, and that's the density, which will, of course, blow up at the end. And you use as a clock the linear density field, delta 1. Okay? So the turnaround corresponds to linear delta 106. This is independent of the initial value of delta. That's why it is used. Okay? And the full collapse will happen when the linear delta reaches 169. Okay? So that's what we wanted to check against. Okay? And then in the process, of course, we analyzed many quantities and their evolution. Let me go fast on this. Perhaps let me just point out that, so this quantity is the one will be constant in linear theory. The dashed line in these plots are linear theory, so that's constant, okay? But this at the peak, so this is the plots at the over densities, okay? The red lines and the blue are the under densities, okay? The peak and the center of the over density and under density, and so you can see that at the over density it blows up. Okay, and then we reach a point where numerical errors dominate. The shaded line is a part is where numerical error becomes very large. So we found that the agreement with the top path at the top. Yes.
Sorry, so this is a very naive question. Just think about the analogy of Schneider collapse. So if I have a bunch of particles that sort of gravitate, of course they will collapse like this. But there's any amount of angular momentum, even a small amount, right, that will just start to resist back.
Sure. Yeah, there is no angular momentum here.
Yeah, so the spherical symmetry sort of assumption is maybe going to give you much bigger overdensity. If there's no perturbation stored in there.
Complicated question. Let me move on. But essentially, if it depends how large is this angular momentum is. Okay. But let me move on. Otherwise, yeah. So we found anyway that at the peak, the tides becomes completely irrelevant, and the peak evolves precisely as a top path. Okay, that's what we found. In the process, we also compute. So this is full GR. Remember, so all this was done in synchronous comoving gauge, but you want to extract nonlinear invariants, and in particular, we wanted to construct the electric and magnetic part of the Weil tensor, and this is the plot. And I think it's very lovely to see that you can see that the electric part is really concentrated along the filaments, okay? And the magnetic part coils around the filaments, okay? Very similar to electromagnets. Anyway, why the top path works so well? So that was the question, okay? Well, the bottom line is very simple, and it boils down to the full Reich-Hardury equation, which is written there, okay? So the full Reich-Hardury equation is coupled in full GR to the shear equation, which is coupled to the electric Weil tensor, which is coupled to the magnetic Weil tensor, very complicated set of full GR equation. But if the shear, and so vorticity here was neglected from start. Okay, we assume in rotational dust, and then vorticity is conserved. If it's 0, remains 0 for a perfect fluid. And the shear, if it's 0, then this equation, guess what, just becomes the standard Friedmann equation. Okay, so therefore, what happens at the peak is that the shear at the peak is negligible. In a sense, is negligible by hand, in the sense that in our initial condition, we assume that this distribution has this tidal field, okay? But the closer you get to the peak, the more spherical it becomes, okay? And so, no surprise, in retrospective, of course, no surprise, you can interpret the peak as evolving as a closed Robertson-Walker, and that's it, okay? So that's me at IUCA in 95 with Rashaduri and Misao Sasaki, by the way. Okay, so this is a cut through the simulation box, cutting from the peak of the overdensity to the left part, to the bottom of the underdensity to the right, and these two plots are at two different times. At the top is the turnaround, and at the bottom is very close to when the ghost crashes at collapse. Okay, this is a fluid. Okay, right. So the main important thing to notice is this: that so first of all, theta is the expansion, the reddish line. Okay, becomes negative at the peak, okay, and that's where the peak is really collapsing. And more important, you can see the green line is the, so these are turnaround, okay, when theta start to become negative, okay. Remember, these are comoving coordinates, okay. So therefore, in these comoving coordinates, the region, the boundary of the region which is collapsing is expanding, okay, and that's why you see that these two zeros here, these are log scale, right? So the zeros of the, when theta change sign are these two peaks, right? And so the inside region is now all collapsing. This is really just before full collapse. And the green line is the shear. So you can see that although the shear, the peak becomes very peaky, right? So the shear is non-negligible, very close to the peak, but then it drops down at the peak, and so the peak is evolves as a top part, okay? Right, let me finish with quick overview of work in progress. This is again with Gramsci's. So again with the full GR M-body code, well, with this approximation. And now the idea is, okay, let's try to repeat with this toy model what was done with the fluid code, okay, but with particles. In this way, we can go beyond the first shell crossing and try to see the effect of tidal fields and the virialization, okay? And again, here is the density field at the initial time. We started with the same redshift. I didn't say that. So both, also the one before, start at very high redshift, 302. So this is the density field, the gravitational potential, one gravitational potential, that's another potential, of course. This is a different gauge, so there are two potential, and that's the vector potential, okay, at the initial time. That's a turnaround. That's okay, now this is particle, so I use the benchmark of turnaround and collapse given me by the linear delta, okay? And so this is when I have this redshift from that initial condition. That's turnaround, so that now is collapse. Okay? And now we can go beyond collapse, and this is at Z9, okay? And you can see that although, oh, by the way, I didn't say that. One goal here is to study the effect of anisotropy at the peak. Because, okay, we get the top path because by construction we use initial conditions which are very spherical at the peak. What if we include anisotropy at the peak? Okay? So that's what we are doing here, and that's why you can see the anisotropy in the distribution, a small anisotropy, which is enhanced, but then is more enhanced at the collapse time, but then you can see in the end at Z9, the central body is pretty spherical, especially in density distribution. Of course, this is work in progress, and much more is needed, okay? And that's the difference between at the overdensity of the isotropic and the anisotropic simulations, and the vertical dashed line correspond to turnaround and collapse. But let me finish with an excursion in even smaller scales, and again with the Einstein toolkit and full GR, okay? And now this is very speculative part of my talk, okay? And we want to zoom in again, even at some very smaller scales, using the same simulation box. We use a mesh refinement to go deeper and deeper, and we also use appropriate gauge because we want to get closer and closer to the collapse, okay? So the various conjectures, okay? Now, once we see these top hat working so well, okay? And in fact, we see that probably the anisotropy, unless it's extremely large, is not dominant. And we know that the top hat is open-Ani Snyder. Is natural, in my relativistic mind, at least, the natural question is, can we form black holes in this way, maybe? So that's one question, and if there is some anisotropy, this relates to another well-known conjecture, which is the Hooke conjecture by Thorne. And in GR, by the way, yes, you have pancakes, but pancakes are negligible in the sense that they are, like in Newtonian theory, it's just a moment, is acoustic in the process, okay? But there are other types of singularities. In fact, pancakes are a set of measured zero in the set of possible singularities. In GR, the typical singularity is a spindle-like singularity. Okay? So we want to see what happens, but more than anything else, we want to see if we can form black holes. After all, James Webb see galaxies at such high redshift, and by the way, in self-interacting dark matter Newtonian models now, they claim that they can see such a concentration that corresponds to the formation of black hole. Here is just dust. I want to just check if just pure dark matter can give me a collapse leading to a black hole, okay? And this is a very difficult problem which we are examining. This is an example where we try to solve it by using 4 blobs of matter rather than 1. Rule of thumb, basically, you can plot, like here, 2m over r, where r is the circumferential radius measured from the peak. Yeah, and I finished with this, okay? And then, as a rule of thumb, and so different blue colors correspond to different proper time from the initial time, okay? So the evolution goes up, and if this, this is a fraction of the simulation box. You can see how small we had to go in the simulation box to see something, okay? And that's why the problem is requires such a very high resolution, okay? And the rule of thumb will be, if you are above line equal to 1, 2m is larger than r, then probably you see a black hole form, okay? Remember, however, we are not in spherical symmetry, so that's why it's very difficult to answer the answer. If we are below, nope, no black hole, okay? The real way to analyze the problem, of course, is to see if you form a trapped surface, okay? Which will be signed by the divergence of the outgoing null vector, and if this is negative, then you will form a trapped surface, and these are 3 plots in 3 different directions. Remember, we had this kind of a tetrahedral structure, which has a diagonal, a face, and the edge, and these are the plot of this outgoing, this divergence of the outgoing direction, and we see something going negative, which is a sign for a trapped surface, but I can't make any claim, okay? Just to show work in progress. Okay, I stop here. Yeah. Thanks for your attention. Is my summary, and I'm not going to repeat.
Thank you, Marco.
But my bottom line is this.
Okay, then. Just one quick question. Keep it short, please, before the...
You showed this result that the back reaction is small but not perturbative. That was using GR n-body simulations? Mm-hmm. How big are they?
That was with the fluid description.
I see.
Yeah, but still full GR. In fact, that's the code which is really no approximation, full GR.
Yeah, the GR might be full, but the fluid approximation does not describe the distribution of matter over scales like below the size of a galaxy, right? So, does it?
No. This is full GR. The simulation box here is several megaparsec.
Yes. Yeah. So my question is, you have not shown that the back reaction problem as described by George Ellis in cosmological structure formation as a whole is, you have not shown that is small. You've just shown some...
I don't claim that that's the end of the story, okay? I could go on explaining why, okay? I think what you are aiming at is that there are very small but very nonlinear structure.
Yes.
Okay, this is not very small, but is more linear than any large-scale realistic structure.
Sure. So I would say that from that point of view, it remains completely unanswered because your numerical relativity does not really go to the relevant scales in the universe.
Well, if you talk about the size, you are right. Yeah.
Okay.
But it could be. So what you are pointing out is this. I reformulate your question more technically. Okay. Is there any up cascading from gravity in GR? Meaning, from small scales, can you produce power at large scales? So far, no. But it's a very interesting question. It's in the back of my mind, and it will require different simulation. Essentially, you will have to do a simulation, say with the same sinusoidal, but instead of a single mode in the box, say the same wavelength, but say the linear scale of the simulation 3 times, okay? And then you could look if that single mode generates an higher harmonic.
Okay.
Okay? That would be the sign of what you are talking about. Okay. I don't think it's going to happen, but that's just, I don't have more than a feeling to express.
Would it be correct to say that the back reaction is just proportional to the variance of the fluctuation on a given, averaged over a given box size? And what you're saying is that on large scales this is small and the effect is small. On small scales it could be large, but you don't know any way to propagate it to large scales.
Yet, in fact, I think Glenn's work was more on that, in that direction, right, Glenn? That is, you looked at the different balls of different size in the simulation box, and when you go on smaller scales, you see a lot of variance. Yeah.
So let's thank Marco again.
Any more questions? Please stop me around. Yeah.
So our next speaker is.
I can just yell, or should I get the mic?
No, don't yell. They will put a mic.
Can I get the mic off?
Oh, yeah.
So our last speaker of the morning session is Subodh, and he will be talking about uses and abuses of effective potentials and fields, field redefinitions in cosmology.
Yep. Sorry, one second. Okay, I should begin by first, reiterating my thanks and gratitude to the organizers of this very nice workshop. It's nice to see some familiar faces again and some new faces, and it's always great to be at the Raman Research Institute. The title is maybe my attempt at rethinking what I have been doing my whole life as a theoretical cosmologist. And certain things started to just sort of pile up on me, sort of puzzles. And I wasn't alone. I think other people started to mutter similar things. And this is sort of my attempt at reconciling them. But I think along the way, I can present some fun things to everybody. I think you'll appreciate. So this is actually a talk in 2 parts. And the second part is based on work soon to appear with my colleague Kunraj Kham and Ana Negro, my former PhD student, who is now working with Glenn in case. So I know she's around very good people. So I'm just going to recap sort of like a schematic of the job description, right? The collective of theoretical early universe cosmologists, right? So the idea is you have some, okay, this is very schematic, please don't take it literally, right? You have some theory, right? I just wrote down a standard model Lagrangian here. You start to calculate correlation functions in this theory on some background given by this theory itself, early phase of early universe inflation. But from that, you start to calculate things that will imprint on the gravitational field. In this case, it's curvature perturbations, and then they imprint on various cosmological observables. We clearly have to go beyond this thing. Okay, some people might argue that Higgs inflation is a candidate, but there's many other things in the 6 parameters in the ΛCDM model that you need to just figure out that don't just follow from this by itself. So the point I'd like to make here is all of these arrows go this way, and the thing is, if you know what you're doing here and you don't make any mistakes, you get a one prediction from this, if you don't make any mistakes. As in, like, you're not going to get multiple answers, right? You're just going to, you have a theory, you get an answer. Observational cosmologists have a much more harder job because the arrows are reversed. If I have a theory, right, and I predict the perturbations, I get some predictions for the correlation. No, I'm not talking about the standard model. I'm saying let's say I have some Lagrangian, I perturb it, I get some spectrum of perturbations, I get some correlation functions, and they feed forward, and I evolve it, right? Yeah. All of these, yes. With all of these assumptions, yes. That's okay. Maybe I should qualify that. Right? You have to, with enough of these assumptions, but in principle, that is your burden, right? Okay. I'm not saying in practice, right? In principle. But the thing reversing these arrows is a much more difficult proposition. Because if you like, and I think the point of the first part of the talk is that actually there are many things going back this way. This mapping is many to one, and this is what makes this job much more challenging, right? So we are observing density fluctuations, we're observing temperature isotropies, we're trying to reconstruct, and I'll try to make precise what that reconstruction entails, certain things, and we're trying to relate that to something. And so what is that thing? Yeah.
Even going the other way, maybe I missed this too.
Yeah.
Same question. You still have to figure out what these are.
Absolutely. You're going to love my next slide. You're going to love my next slide. Don't worry. It's all in there, right? No, I agree completely, right? So, but I mean, in principle, right? There's a lot of things going on, including what that state is, right? So this is just a schematic, right? I mean, I'm setting up my where I really want to go with this, right? So view it as sort of like a forward modeling process, right? So, okay, so the thing is, we assume that there is a scalar degree of freedom. This is a restriction. It's a prior that I put in, a theoretical prior. There are motivated reasons for it, and I have some effective Lagrangian. Of course, I could have added curvature squared. I write down everything, but by exploiting operator redundancies, I can bring them into this form. And then the forward modeling consists of realizing that actually, if I only have a single degree of freedom, I can just sort of reparameterize my clock to absorb the perturbations of that degree of freedom into the so-called curvature perturbation. And the job then is to go on ahead and calculate correlation functions. And so really in a slide, right, I mean, there's a lot of things I think we're all aware. There's a lot of assumptions, there's a lot of things that go in, assumptions of isotropy, assumptions of what this state is, a theory that in principle you perturb that gives you these numbers, and then you got to run them through a bunch of transfer functions. You have to evolve them forwards to give you the various observables that you want. And so these transfer functions, of course, have an irreducible geometric compression. If you're looking at a two-dimensional anisotropy field, the matter power spectrum does not necessarily have the same level of compression, although it is there, and then there's some non-primordial cosmological evolution. So if I just focus on the anisotropies, all cosmological observations to date are consistent with adiabatic, Gaussian, nearly scalar invariant initial conditions. To me, they are evidence of a particular symmetry breaking pattern in the universe with a close to vanishing derivative coupled order parameter, the epsilon, which is one in a tower of Hubble hierarchy parameters, and it is widely accepted as a confirmation of the inflationary paradigm. So if you're someone like myself and you're sort of trying to ask the question, well, what could that teach us about what was really happening, at the beginning? Can we know? Can we actually have an ontological understanding of, what is knowable? The question is, if the inflaton is a real physical degree of freedom, might there be other scales of correlations hidden in the data? So you can go looking for these. This, I don't want you to take literally. I want you to take this as an engineering challenge, right? So if vanilla initial conditions are all there is, what could we possibly learn about the inflaton as a physical degree of freedom? Is it possible? Is that even a question you can actually get some credible information of? So
The issue, if you're just stuck with temperature anisotropies, which thankfully we can go far beyond now, the problem is you then have to deal with nonlinearities. Nonlinearities are very good at erasing initial condition information. So you win some and you lose some there. But if I just stick to what I'm seeing in the temperature anisotropies, the CMB transfer functions are geometrically compressing primordial data. Really what it comes down to is you're trying to reconstruct a three-dimensional field from a two-dimensional slice. So unless you start putting in more priors, that there's roughly a scale invariance, you're not going to be able to say as much. But we think that's very well motivated, so we proceed. But could there be new physics or new characteristic scales hiding in plain sight? I don't know. But I would like to stress that the perspective that I'm about to, if this is unfamiliar, I'm sure this is quite familiar to many people in the audience, but if it's unfamiliar to you, then the perspective that follows is elaborated upon in this review. And the idea is, if you're a particle physicist, you can actually view this curvature perturbation as a Goldstone mode that non-linearly realized the time translation variance, or if you like breaking time translation symmetry, the counting for breaking space-time symmetries to the number of Goldstones works very differently. You have these things called inverse Higgs constraints and so on and so forth. But the idea is that you can forget about your background and just now be looking at the theory of the perturbations that in principle encodes it, and they're encoded in these functions now, functions of time in principle. Where this epsilon, the first parameter in the Hubble hierarchy, is sensitive to changes in the 0 and 2 derivative terms in whatever parent theory you think you perturbed. Then there's this other thing, the speed of sound, that is sensitive to 2 and 4 derivatives. And then there's this other term that is in principle there, but it is going to be subleading at long wavelengths. So we can justifiably ignore it. If you go to talk to the SMEF people, the Standard Model Effective Field Theory people, what they're trying to do is they write down, so if you took all standard model operators and constructed all possible dimension 6 operators, out of it, there's 2,400 and something, 60-something possible combinations. That's a lot. But if you impose that, so if you're going to go and ask, can you go and fit for 2,400 constants from collider data, it's quite tough. So they make another assumption, which is, okay, maybe flavor is conserved, seems reasonable. Then you're down to 59. And so then what happens is you sort of look at collider experiments and you look for deviations from your prediction that are sensitive to these coefficients. And this is the game of collider phenomena. So far, no evidence. You could do the same thing for cosmological data, and you could try to reconstruct the data and try to arrive at what are rightfully should be called Wilson functions, because they're not constants. They're functions of time, because you've broken Lorentz invariance, or spontaneously been broken by the background. So I think everybody understands that the scale dependence of the cosmological correlation functions is induced by the time dependence, or the very weak time dependence of these parameters, this epsilon, the speed of sounds. And that scale dependence is encoding this time dependence. It actually turns out that you can, just like you tried to do in a collider, you can invert, quote unquote, because it's not unique, but it's an engineering problem. You can invert for these Wilson functions given a spectrum. So I am not saying that this is something you should take literally. I am saying, what if I took this wiggly curve literally and asked the question, so this is a proof of principle. I'm not saying this is what I think is actually happening. Can I write down a Lagrangian that gives me this? So yes, and then I will critique it and make fun of myself. But you know that if you, so again, so I'm just going to pile on the priors and say, okay, I'm assuming that the speed of sound stays 1, but I'm assuming that there's something about the first Hubble hierarchy parameter, epsilon, that is varying in time. That time variation is going to imprint features in the primordial power spectrum as follows, in a manner that can be inverted. So if I see a feature, I can invert, it's just an invertible integral transform, I can invert for the time dependence of this epsilon to first order. You can actually do it to second order. And I actually had a bit of a flashback when I was writing up the slide, because I actually was doing these principal values over there. It was in 2019. I was at a workshop at ICTS, and Ravi Subramanian, the former director, kindly put me up here because there was out of room up there. So you can actually do this inversion only for this epsilon parameter to second order. And it turns out that it's the square of the first. It's a very nice relation that's not true if you start to look at deviation from the speed of sound. But the idea is now you can actually figure out how to do this inversion to second order. So what have I done here? I have, this is kind of nuts, but I just want to point this out as a weird engineering problem that we worked out. Imagine someone gave me the challenge, hey guys, can you give me a potential that threads the needle and nails all of these wiggles? And the answer is yes, I can by this inversion process, and this is it. That's the potential. One of them is the slow roll attractor. One of them is the one with the varying epsilon. This is the potential. Looks kind of the same until I look at its first derivative. Okay, fine, right? So what I've done is I've kind of knocked around, you know, the potential, the field as it's rolling down off attractor such that I nail all these wiggles. The point is that, you know, depending on all the priors I put in, I'm able to curve fit arbitrarily. Not particularly enlightening. But it's a proof of a principle that I just wanted to state here, which is that this can be done. And so it raises the question, and this is where I'm going to sort of come across the real point of this, which is, can you engineer arbitrary potentials to get whatever spectrum you want? This is a question that I've been struggling with for some time. And by the way, this is not unique. This is not a reconstruction. You know, this is just saying if I just see something and then I ask, is there a model that you can push forward to reproduce that? And the answer is yes. It's a post-diction. And to answer the question, can you engineer any potential to get arbitrary spectrum you want? The answer is no. I think everybody kind of has some understanding of this, but I would like to actually luxuriate in this by first thinking about what we're doing a little bit more carefully. So these are two Lagrangians. Has anybody seen these two Lagrangians before? Can I get a show of hands? Glenn has. So Glenn, I'm going to ask you to not answer this question, but so is it just Glenn? Surely other people have. Yes, Mustafa. Okay. So for those who know where I'm going with this, right? And by the way, this is actually, you know, so I think one must take time to luxuriate in life's small pleasures. When I learned this, it blew my mind. One of my favorite things to do as somebody in the state of life that I'm in now is to, I do this at a blackboard with all of my students, and when I tell them this, I just watch their eyes light up. These are the same theory, okay? One of them, in 1+1, is a theory of bosons and the cosine potential. The other one is, in 1+1, a theory of fermions, Dirac fermions with a 4-Fermi interaction, which actually happens to be normalizable in 1+1. How do I, if you look at this theory, okay, it looks like it's a scalar field and a cosine potential, but you know cosine potential has various minima. The thing is, I need to know that the field at one place and the other place at minus infinity has to go to one of the minima. So I could go from minima A to minima B, from minus infinity to infinity. I could go from minima B back to minima A from minus infinity. I have basically a series of an infinite number of undeformable solution solitons. What happens is if I fire in from the left and right, the two solitons with the same charge, they kind of bounce off each other. If I fire them in with the opposite charge, they annihilate. They look like fermions, and in fact they are. These two theories are the same theory. This was proven by Skirm. Well, Skirm conjectured it, that this is actually true. And you have to understand what a remarkable statement this is, right? I've written down a theory of bosons, and this is a theory of fermions. They are the same theory, okay? It's been proven both at the operator and the Green's function level by Coleman and Mandelstam, and these are the relations. They are literally the same thing. What happened? Well, it's actually really cool. It's called bosonization, and the statement there is you saw a classical Lagrangian. Now, if you go back to this Lagrangian and you try to perturb around harmonic oscillator, so you know you say, okay, it's an m² phi squared potential. Let me just perturb around the minimum. And you start, but it's interacting. You start calculating loops. Those loops are starting to get really, really intense. It turns out that maybe you should have actually expanded in a basis of solitons instead. And this is the concept of so bosons can turn into fermions, okay? Or really, the reality was always fermions, but because you never see the classical reality. But the thing is, if you wrote that down, your theory is flowing to something that is very, very different. Quantum mechanical fully addressed degrees of freedom can look nothing like your classical degrees of freedom. That's the moral of this story. If you look up a review article on effective field theory by Anish Manor, he begins with this as a caution to people from taking Lagrangians literally. And what is happening is this thing called dimensional transmutation. This operator, which is dimensionless, flows to this 2 Fermi bilinear under renormalization. And I think I just want to just sort of stress what that looks like, if you'll just humor me. So this is, to me, one of the most spectacular and beautiful things about quantum field theory that everybody should really appreciate. So if in 4 dimensions, so this isn't 1 plus 1, so I'm just going to make a schematic of what would happen in 4 plus 1. And again, I don't have a theory to do this, but I just want to explain what this word anomalous dimension means in case you ever come across it again. If I look at 2 fermions, a correlation function of 3 fermions in 3 plus 1, you're going to get a correlation function that looks linear in the relativistic distance, plus something with a slash structure to take into account its tensor structure. If I did the same thing for free scalar, I'm going to get something that looks like, again, there's some number here, x minus x prime squared. That's just a relativistic, I mean, this is very straightforward. You can calculate it, and this is what you get. Now, this is a free theory. Imagine I have now turn on loops. I have an interacting theory, and I calculate the 1 loop answer, and I get something, 16 pi squared, and I have a log, right? But so now you're used to seeing these things in Fourier space, but I'm Fourier transforming them back. There's a log over here, but then I realize, actually, hang on a second, I can take this log and represent it as a little deformation of this index, where delta is equal to lambda divided by 16 pi squared. This is what is known as the anomalous dimension in effective field theory. This is what we have to calculate when we calculate loops. So that was 1 loop correction. Imagine I have a special theory where I can just resum all of the logs, and this number becomes 1. And that's what's happening here. Okay? When this number becomes 1, you have a correlation function that looks exactly like fermions. My degrees of freedom have morphed. So this is a really special thing, and it's to be paid attention to about quantum fields, right? Is that what you see isn't what you get in the end. So I bring this up to you to highlight a thing that I had to struggle myself. Okay, so this this is me. This is Subodh trying to make sense of something he did in his career and decided to walk away from. So this is that story. Not about effective potentials, right? So not everything about effective potentials are physical, actually. This is very well known. Aside from the values of the critical points, even the standard model effective potential is gauge dependent and next to leading order. This is also known. But at the critical points, i.e. where you can do background field quantization, everything works nicely, everything's consistent, all the U things that you put in drop out, you get physical answers. But it's also known that the true effective potential is strictly convex. And this is chapter 11 of Peskin and Schroeder. What does that mean is that you can have a classical potential, but if you loop correct it enough, and it's a very nice demonstration of this in a nice paper by Juno Krohn and collaborators, where they actually show this procedure. If you loop correct enough, what you thought was a wine bottle potential just becomes flat completely. And this is very, very well understood. Eric Weinberg, so Eric Weinberg so this is an accounting by Eric Weinberg. This is very, very well understood, and the statement simply is that there are some things you can use this picture for, i.e. calculating tunneling rates, and so on and so forth, but there are other things you cannot. What it's really telling you is that everything in here is an unstable saddle point of the path integral. And what your phi field in this region is actually doing is bookkeeping an order parameter in a spinodal transition between these two phases. Spinodal means there's no latent heat going through them. So background field quantization around an unstable saddle point obviously makes no sense, but the way to think about values of the potential away from the critical points in a non-convex potential is that it's just bookkeeping an order parameter. But I wouldn't quantize an order parameter. It's like trying to quantize around a fractal. What are you doing? So, I'm not saying what we've been doing in cosmology is wrong. I'm saying clearly something is making this theorem not work. What is it? okay? So loopholes, ways out. There are many, right? One of them is large occupation, right? This is a vacuum statement. The possibility of either the photon itself or something coupled to it is classically driving it, right? So there's something, so anything classical you should just think of as a large occupation state on a quantum expectation value. This is not true in that case. Boundary effects, so boundary effects do actually make this change. Jean-Alexandre in King's College has been working on this quite a lot. Particle producing classical driving threshold phases, there's all sorts of things, but all of them require the accounting of additional degrees of freedom close to or lighter than the energy scale in process, i.e. there's something else changing at the scale at which you're interested in. So if there's anything that strictly relies on an adiabatic evolution, you have to maybe account for the possibility of additional things pinging around. Now, for the most things that we want to calculate inflation, I don't think it really matters because isocurvature perturbations just go away, right? But if you're trying to sort of do things like primordial black hole formation, where you really, when you start to count isocurvature perturbations and your calculations are off by orders of magnitude, maybe you want to think about it again. So I stopped thinking about them after this, okay? But I think the moral of the message for myself, take it for what it's worth for you, is you actually, as a theorist, you may think, so the reason I went to this exercise, it might seem flippant, but I intended it to serve a purpose, which is you're not free to just design any function you like. There are rules. And if the observational cosmology job is so hard enough already, you want to be giving them models that satisfy strict theoretical priors of self-consistency. And it just makes their job easier. And I invite people to please think this way. And so there's more, right? And I think everybody can kind of wrap. So this actually came up, and I actually had some really amazing discussions with people where I'm just like, oh my God, like, do you really think like this? But and this is sort of my sort of just sort of thing that I have to show people just to say, look, please stop just saying words, calculate something, right? The things that imprint on your correlation functions are in the effective theory of the adiabatic mode. They're functions of time that come from, in principle, perturbing something that is coming from a consistent derivative expansion. So controlled derivative expansion is going to give you constraints in the temporal variation of these things. You can't make them wiggle around arbitrarily. So I have many examples of this, many, countless. I've shown them to people, be like, guy, this is your papers, you can't do this, right? But they're like, no, there's something else that does it. It's like, no, this is not how it works. But I will just show you a simple one that I think is easy enough to wrap your head around, which is, is there a quickest possible end to inflation? This one's so simple and it just follows from the mean value theorem of calculus. If I take the equations of motion of inflation and I work in E-folds, the equation becomes this, okay? And I can use the mean value theorem of calculus to then, so what I'm saying here is that I've had the background from epsilon go from 0 to basically whatever ends inflation. I forget the number, at least 1. So if I demand a change in epsilon to be such to happen over a particular number of E-folds, I get this bound. So if I decide to just stick a representative potential in there and ask, okay, and by the way, this breaks all the rules that I was just talking about, but let's just go with it. And I ask, okay, can I get inflation to end in less than 100th of an E-fold? And the answer is, you would have to make this scale 10 to the 2. You have a crazy mass scale here, which is very weird. You would never expect this to be a consistent derivative expansion. This would be completely annihilated in loops. I mean, this would, okay. It's just renormalization group improvements of this potential would smooth everything out and mix up scales. If I were to ask the question, can I end inflation in 1/10 of an E-fold? Then you get to this order 1. And I would argue that's still a little tough. The funny thing is, if you go back to the original paper on instantaneous preheating, these guys knew, right? But they don't flesh it out into such detail. Kaufman and Linde say, like, yeah, instantaneous for us is 1 E-fold. 1 E-fold is instantaneous. You cannot get anything less than that. There is a proliferation of papers in the literature where, they're like, so the big confusion is people think you can get arbitrary mass scales to happen, make something happen arbitrarily fast in time. That may be true, but it's not good. It's going to cost you E-folds. Anything you make sudden in time costs you gradients, gradients cost expansion. It is very difficult to get the E-folding to be less than 1. And that's what you imprint in your features, in your observations. So inflation, so the moral of this part of the talk is that inflation is hard enough to get, okay? But the thing is, what's beautiful, and this I think is a spectacular accomplishment of theory. the theory of the perturbations is determined by the symmetry breaking pattern. And in fact, we may not even have any idea what in the inflaton was. It could be some strongly coupled holographic phase where we can't even write down a Lagrangian. Doesn't matter. The theory of the perturbations, those Wilson functions you calculate, is determined by that symmetry breaking pattern. And that's what we need to connect observations. And if you're looking at something from a model building point of view, it's this shift symmetry that protects inflation, and that's what's giving us this almost scaling invariant spectrum, except up to an expected and weak logarithmic running. Nice. Breaking this shift symmetry over a small field range is dicey, because you have to introduce additional hierarchies. And on top of the one already required by inflation, which is hard enough to preserve. So, and you have to show that these survive RG improvements. It's not negotiable. So I've actually stopped myself doing this. I think that the challenges are many, but I'm not going to ever write down another model again that does something other than unless I get strong evidence that there is a characteristic scale. So I would like to really maybe ask the question: can we extract this somehow from the data? That's the thing I'm more interested in these days. So that was part one. Part two is actually something else that I started to get murmurings of, talking to people. They sort of said, hey, have you noticed this? Yeah, I noticed this too. What's going on? Okay. And it's about what we traditionally think of as the adiabaticity condition. I'll go through it in a second. How it's necessary but not sufficient, actually. And in order to understand what is going on, so I'll show you a counterexample, which I think is so easy to understand, and I think you will just realize that we need to think a bit harder. But in order to diagnose this counterexample, we actually had to come across something that we're still not really sure of, but I will point it out to you. So adiabatic evolution is that if you have a state in some eigenstate and you change the parameters of the Hamiltonian, whatever that Hamiltonian evolves to, you kind of just juggle and balance that state and it stays in that eigenstate. Okay, so this is if you like the definition of adiabaticity. There's none other. Okay. So what that means, if you have a state in the initial vacuum, it involves to the vacuum at that point. I.e., if you took their overlap, it could at most be a phase. That phase is a very cool thing. It's the generating function of all one particle irreducible vacuum graphs. You don't need to know that, but it's a very nice thing to note. And so the non-overlap of this, i.e. if this is anything other than a phase, implies that this thing must have an imaginary contribution. Yeah, which you can actually take as the definition of particle production, and it often is. Okay, and so then if you happen to have a field basis which you can calculate, it relates to the sum over all P of all the Bogoliubov coefficients that you generate in this process. So taking that as a definition of particle production, it is often, and I think I've seen this everywhere, what is this thing? This is actually the leading order term in a WKB approximation that has now somehow been elevated to be the definition of non-adiabaticity. They are not the same thing. In terms of field modes, adiabatic evolution, or the absence of particle production, is often quoted as being equivalent to this condition. And what follows, I will critically re-examine the law that this is true. It's not true. Okay? I'll show you via a counterexample. I'll try to understand what could have gone wrong. I will go back and explain what the equivalence theorem is, and point out something that makes me very stressed out, actually. But I'm not saying that, I will try to resolve it myself as well. But I will also point out that we are not actually noticing anything new. It's actually been noticed by other people as well in a completely different context, and just summarize that and conclude. So this is a counterexample. And the thing is, I'm about to do a bunch of things that we do without blinking in cosmology. Free scalar field on Minkowski space. I think we all agree there's no particle production. Minkowski space is stable. It doesn't annihilate, doesn't disappear. It's a vacuum solution of Einstein's equation. It just stays there forever. But in a covariant theory, we're free to make coordinate reparametrization. So consider a time reparametrization, like we do in the effective theory of the adiabatic mode. When I do that, I have a fake metric. I mean, it's still a Minkowski metric, just written in a funny coordinate system. Of course, I'm going to put some conditions on F that never vanish to become negative, i.e. I preserve global hyperbolicity of whatever coordinate system I have. And then I say, oh, cool, okay, let me just make this field redefinition. I just absorb this, so it's a non-canonical connector. I just absorb it and then redefine things that, oh, look, I have what looks like a effective frequency for when I quantize these modes, which I can engineer to arbitrarily violate the adiabaticity condition at will. for something very, very nice. This thing just literally is a time-dependent reparameterization. It's just a rescaling of time that just goes from one to something else that just changes by this rapidity. Okay, so undercooked. So obviously, and by the way, I have another example. I said for some of you might see, I had to, so this is actually 3 talks spliced together, so I may have some ghosts from another talk. So there are no magic contributions to effective action, obviously. Minkowski space is stable, in spite of the adiabaticity condition being violated for some modes at some time. But notice that I was very cavalier about 2 things. Number 1, making space-time dependent fluid definitions hoping matrix elements won't be affected was 1. The other one is, I mean, I think I think we've all been doing this to the point that we've forgotten. I think I was very sloppy about what exactly I mean by omega and dot, right? I just did a time reparameterization. So like, you know, general relativity should be a theory that doesn't care about physical conclusions based on coordinates. So maybe there's a covariantization of this statement I should really be looking at instead. This is our process of trying to diagnose how to resolve that counterexample. And I had some really amazing conversations with some very clever people, and I learned a lot. The equivalence theorem, I will actually show you this in the context of regular statistics. So this is actually a kind of a nothing burger statement, but it looks complicated here, but let me just stress. I can take a field and make an arbitrary field redefinition, and I'll have the same S matrix elements. Okay, so if, for example, I had a free scalar field in Minkowski space, right? So the action is just this, d mu phi, that's it. Right, but now I say phi is equal to f of psi. Psi is some complicated field. Then this becomes something which is 1 over 2 f prime d mu psi, and this is psi. So now I have a whole bunch of interaction Lagrangian terms, tons. Cubic, quartic, all I want. Magic things happens when I try to look at psi scattering. And I sum all the diagrams, and they sum to 0. Obviously, it's a free scalar field. It's not interacting. But you wouldn't have known that if you're just messing around with Feynman diagrams. They sum to 0. Quickly, you learn something more special is happening, and it's equivalence theorem. And it is this statement. These 2 partition functions generate the same on-shell S matrix elements. It's not as complicated as it looks. Okay, everybody can understand this, right? But what makes it complicated, I'll first explain it. So if I just have a regular probability distribution, I know I can generate all moments by just introducing this source and taking derivatives with the source. I get all the correlation functions of x. But now, let's say I decide to make a random field redefinition, i.e. a change of random variables. Then I know that the new probability measure has to be expressed by this. I then ask the question, had I not known this and I just stuck it and I constructed the generating function for this new random variable, a series of manipulations leads me that it's actually equivalent to calculating PDFs in the old variable with a shifted source. And that's this statement, okay? That's all there is here, but then making a redefinition back. It's a bit more complicated because we don't have normalized probability distribution functions, and there's a continuum, and you have to redefine fields. And in quantum field theory, you don't calculate probabilities, you calculate amplitudes, you have to square the probabilities. That's why it makes it hairy. But if you ever want to understand the equivalence theorem, just go back to this. It's kind of obvious. So consider a field redefinition form of this form. It is a extended canonical transformation, scale dependent. Now the standard proofs, i.e. by the generating function or the LSE reduction formula, only work when the proofs that we try to follow only work when this function has finite space-time support. This does not have finite space-time support, right? There's a Fourier integral. And by the way, this is the same mathematics, by the way, beyond spontaneous symmetry breaking. You will find a non-overlap between the vacuum of one theory and the other. They're just in different Hilbert spaces. This proof breaks down. We don't know what to do. So I'm just going to park that there. I'm not going to give you an answer because that's still something we are debating. But all I can say is I cannot prove that these theories are quantum mechanically equivalent until this condition is satisfied, which it isn't for the field definitions that I just used and got into trouble. So let me just park that for a second and point something else out, which is, okay, let's just keep going and say, well, what would the right condition be in general, right? So the statement that this is actually a statement about the validity of the WKV approximation. But adiabatic evolution literally just means you do not change from one eigenvalue to another as you time evolve the Hamiltonian. So the thing to do might be to find a covariant generalization of this, but actually, even in quantum mechanics, so these people who work on adiabatic quantum computation realize that it's not sufficient either. So these are a bunch of conditions that even in a quantum mechanical system, you have to take into account. And they're integral constraints, which are not nice, actually. So it might seem like, you know, the thing to do would be to make the field space covariant, the space-time covariant generalizations of these. But they're a very ugly and convoluted set of conditions. But along the way, we've learned that a common manipulation undertaken in many cosmological applications requires additional care. That's all I will say. I'm not saying that, you know, one thing is wrong or the other, but I'm a simple person, right? If I have a bunch of rules and I find something I have to break those rules to get out of, I need to think a bit harder. So yeah, so in fact, I think that is, I think that the strong version of the statement here is that those field definitions are illegal, actually. I would like to say that, but I would like to check a few more things before I make that statement. Which isn't to say we're making mistakes in cosmology. It should just be like, please, please, please only make a field definition in the absolute worst case scenario. Like, just try to avoid them, right? Because they're inequivalent quantum theories. This is very well known. We're seeing it laid bare here. More details to follow in this. And yeah, thanks for your attention.
Questions to the speaker?
So I guess what you're saying is well known, but I guess I didn't know it, which is that if you do a Higgs symmetry breaking potential, then you shouldn't use an effective potential. Is that
No,
what?
no. So there's things you can calculate from that, right? There are certain things you can calculate, like tunneling rates and everything. That's a fine thing to do.
Let me put it another way.
Yeah.
Do you put it into the field equation,
Yeah.
phi dot dot, or do you not, or do you have?
So,
to
so
put it
I would say
directly?
if I'm treating that field phi as anything other than a classical background that I know is an unstable saddle point of the equilibrium, I'm looking at correlation functions of quantizations of that field around that point. I would say there's other ingredients there, but that in the things that we're calculating, the additional ingredients won't change that much the answer that I'm worried about. But if I'm relying strictly on adiabaticity, then I would be a bit more worried. I'd check a few
So,
more things.
or let me put it into,
Yeah.
I use the Higgs words, good words.
Yeah.
But let's go to Ginsburg-Landau.
Yeah.
So we're into a
Yeah, so there's-
known
yeah.
system of
Yeah. But
condensed
that evades
matter.
this. That evades this, right? Because it's
So
large. There's a classical thing that's making. There's a large occupation number, something that's making that modulation there.
So you're saying it's a consequence of the near classicality of that case?
This theorem is strictly vacuum, right?
Well, no, I understand,
Yeah.
but you're imposing an effective, I mean, I am in complete agreement that effective potentials should not be done the way they're done.
Yeah.
So I agree with that
Yeah,
completely.
yeah,
In
yeah.
fact, I was singing that story in the inflation meeting last week in
Yeah.
Paris. But it's not clear to me that you've got the mechanism to check all of that, because really, the effective potentials flow along with the
Yep.
medium.
They get RG improved. Yep.
And so it means that you have to have the two going together, and
Yep.
nobody does that. But they should do that.
I completely agree.
And so I just have one other issue.
I just want to flash the loopholes though, right? So the thing is like, yeah. So the thing is there are ways around it, right? And I think in a lot of applications they're there, right? What I mean here is this is the strict.
No, I agree with the
Yeah,
PBH
yeah,
extremity. I
yeah.
completely agree with that. Okay, so I want to ask one more question. Sorry about this, but it's a highly significant one because
Sure.
a lot of attention
Yeah.
has been paid to the oscillations in a monodromy potential.
Mhm.
And then you try and find the frequency by seeing pattern
Yeah.
matching in the data.
Yeah.
And am I hearing that that is a failed effort?
No,
because-
classical driving, right? So there's a thing with a large occupation number, right? Which is the thing.
Well, it wasn't really a large, it's not that, it's just a
Yeah.
winding up
So there's a thing with a very so the thing is
modified cone.
yeah. So the way so.
or
I
cylinder.
won't overcommit. I would say that in that case, I can imagine how it's okay because the thing is, I would think of any sort of large sort of expectation value of a field that I treat classically as a state that's not vacuum veved around a field operator. And then that would make this analysis no longer applicable, right?
Yeah, but I don't think that's how Eva was doing it. That was.
It could be a use, the people who.
That wasn't the way it was being,
Yeah.
at least somebody else may know better.
Yeah.
But I mean, what I'm trying to say is that
Yeah.
if there's a real issue here and you've got it,
Yeah.
you have to tell the people who are doing C&B analyses so that
Yeah.
you can fix the story.
Yeah, look, so I may have lost a collaborator in this process because we were writing a paper and I was saying, hey, you just can't do this, right? And I will say this, so even the question of renormalization group improvement, I have RG codes, right? Actually, the beta functions are known to all order for a scalar field, right? It's just a combinatorial problem. And I tried to run it. The problem was, when I tried to actually perturbatively Taylor expand around a field point, around anything interesting happening, those coefficients are already 350,000, 450,000, right? You can't get anything other than something very, very gentle. So imagine you try to have like a break, right? You try to do like let's say you try to do Starobinsky potential, something like this, or the thing is like, what renormalization group, so I learned all of this. I gained a lot of respect by actually trying to calculate the two-loop RG improved Higgs potential, and wow, like it's so hard to get anything, like the renormalization group running does what it does depending on the parameters, but if you then start messing around with the potential, those scales mix up. So yes, I agree that's the burden of proof on the theorist. And I'm not convinced most people do it at all.
Yeah, well, I think there's a big project here.
Yeah.
I think the project has not been done. I hope to dive into it
Yeah.
myself, but it'll
Yeah.
be interesting to check.
Of course, yeah.
So may I kind of get to this last part of your talk? I think I completely misunderstood. I didn't understand what you were saying. It seemed that you gave an example where omega dot over omega squared is big,
Yeah.
but then the system is adiabatic, right?
It's a free scalar field on Minkowski space.
So it seems that you're saying that this is not a necessary condition, but it
Yeah.
doesn't say it's not a sufficient condition. So there's
No. So okay. Sufficient means this would be enough to prove particle production, right? I would say that if you have a covariantized version of that statement.
No. I think you're reversing this. Omega dot omega over omega squared much less than 1 says that there is no particle production.
Yeah.
So this goes one way, not the other.
No. So omega dot over omega squared greater than 1 means particle production.
Well, but that's not what you wrote there. You wrote
Okay, well
less
then
than 1.
okay, so
But it just
No.
the other way doesn't work.
No, hang on a second. No. This is just a simple logic point, right? Is that if something is not true, if something, then something opposite. Okay.
No,
If
it goes
omega
the
dot
other
over
way
omega
around.
squared is greater than 1, almost everybody would say that is particle production.
No. Obviously, you have transparent potentials
Yeah.
that there's zero reflection from them, even though they are big. And that's an example of that. That just because omega dot over omega squared is big, that doesn't mean that you get particle production.
Great, then I don't need to convince you. But you will see that statement in the literature a lot.
Okay, so then it's wrong.
Yeah. But this is the statement we're addressing. Yeah.
Can I say this
Yeah.
another way?
Yeah.
What you've written down,
Yeah.
if we put instead of, if you put down instead of omega, you put down h.
Yeah.
Then you've written that epsilon has to be small.
Yeah. So in that
And
case, yeah.
that's not the issue.
Yeah,
The
yeah.
issue is the change of epsilon,
Yeah.
which is breaking down the
Yeah.
adiabaticity.
So no, but that's
it's an
adiabatic
issue-
in the
it's an
cosmological
issue of
sense.
Basically an epsilon.
There's two
gradient.
terms to adiabaticity. So in cosmology, we mean one thing by adiabaticity. So this is the actual adiabatic theorem of quantum mechanics. They do relate to each other often,
No,
but
it's
they're not
exactly
strictly the same.
It's
Not-
exactly the same.
not
One's a
always.
damping coefficient
Yeah.
and the other one's a frequency coefficient, but it's the same story. So it's going to be.
So
that-
you can actually have a very minor
that
amount of particle production
coefficient will
in
have
one
to
field.
Change in time.
Yeah.
Rather than being uniform. If
So,
it's
so
uniform,
epsilon is a
then you
statement about
aren't
the
gonna get a
gravitational
breakdown of
background. So I can
adiabaticity.
actually violate the adiabaticity for a field, but it's still not enough to change the background. So epsilon is still very smoothly, but that field is violated adiabaticity, right? So it's a separate statement.
Well,
Yeah.
at least
Yeah.
it's not an inflation.
Yeah, well, yes. If it's only inflation, that's the only thing hanging around, right? But there is actually a slight, what we mean in adiabaticity in cosmology is single clock, really, right? What we mean by adiabaticity in this context specifically is the preservation of the eigenstates of Hamiltonian under time evolution.
It doesn't have to be a single clock, it's just that the epsilon is defining a direction.
If there are no further questions, let's thank Subodh once again and all the other speakers of the morning. So we will reconvene at 2:30 here for the afternoon session.